Before Max Planck entered the world of physics, science was filled with confidence, structure, and a strong sense of completion. By the late 19th century, many physicists believed that the fundamental laws governing the universe had already been discovered. Nature, they thought, was like a perfectly designed machine, operating according to predictable rules that could be expressed through precise mathematical equations. This period is often described as the golden age of classical physics, where certainty seemed stronger than curiosity. At the heart of this confidence stood the achievements of earlier scientists. Isaac Newton's laws of motion and gravitation had explained how objects move on Earth and how planets travel through space. James Clerk Maxwell's equations unified electricity, magnetism, and light into one elegant framework, revealing that light itself is an electromagnetic wave. Together, these theories painted a picture of a universe that was continuous, smooth, and orderly. Energy flowed without interruption, time moved steadily forward, and matter behaved in ways that could be measured and predicted with great accuracy. This sense of completeness was so strong that some prominent physicists famously claimed that the future of physics would involve only refining measurements, not discovering new principles. Young students were even warned that physics had little left to offer in terms of groundbreaking ideas. The discipline appeared stable, logical, and almost finished, but this confidence would soon prove to be misleading. Beneath the surface of success, small but persistent problems were emerging. Certain experimental results did not fully agree with classical theories. These inconsistencies were often ignored or considered minor technical issues that would eventually be resolved. After all, classical physics had been remarkably successful for centuries. Few suspected that these small cracks were signs of a much deeper problem. One major area of concern involved heat and radiation. Scientists were trying to understand how objects emit energy when heated. According to classical ideas, a heated object should emit radiation across all frequencies, with the intensity steadily increasing at higher frequencies. Mathematical models based on classical physics predicted that as frequency increased, the emitted energy should rise endlessly. However, real experiments showed the opposite. At high frequencies, the energy dropped sharply instead of increasing. This contradiction created serious confusion. This mismatch between theory and experiment revealed a fundamental flaw in classical thinking. The equations that worked so well for planets, projectiles, and electrical circuits failed when applied to microscopic phenomena. Classical physics could not explain why matter and energy behaved differently at small scales. The universe was no longer behaving like a smooth machine. Instead, it seemed to hide rules that scientists did not yet understand. Another troubling issue involved the nature of light. While Maxwell's equations described light as a wave, certain experiments suggested particle-like behavior. This contradiction challenged the idea that light could be explained by a single, continuous model. Classical physics struggled to reconcile these opposing observations, and no satisfying solution emerged. These unresolved problems created an uneasy tension within the scientific community. On the surface, physics appeared complete, but underneath, it was quietly breaking down. The theories that explained the motion of stars failed to explain the behavior of atoms. The laws that predicted the flow of energy could not describe how energy was actually emitted. The world of the very small was slipping beyond the reach of classical explanations. It was in this environment of confidence mixed with confusion that Max Planck began his work. Unlike revolutionary thinkers who actively sought to challenge existing ideas, Planck deeply trusted classical physics. He believed the laws of thermodynamics and electromagnetism were fundamentally correct and only needed refinement. His goal was not to destroy the old framework, but to repair it. Yet history often advances not through bold rebellion, but through careful honesty. The scientific world before Max Planck was standing at the edge of a hidden revolution, unaware that its most trusted assumptions were about to be questioned. Classical physics had reached its limits, and the universe was demanding a new language to describe its deepest truths. This moment in history is crucial to understand because it shows that scientific progress is not always driven by certainty, but by doubt. The confidence of 19th century physics made the shock of quantum theory even greater. When Planck introduced his radical idea, it did not merely add a new equation to science. It shattered the belief that nature is always continuous and predictable. The world before Max Planck was orderly, elegant, and reassuring, but it was incomplete. It was a world that could describe motion and energy on a large scale, yet failed at the smallest levels of reality. This fragile balance between success and failure set the stage for one of the greatest transformations in human understanding, proving that even the most trusted knowledge must remain open to revision. Max Planck's early life offers deep insight into the kind of man who would later ignite one of the greatest revolutions in science. He was not born into poverty or struggle, nor was he shaped by dramatic rebellion against society. Instead, his upbringing was marked by discipline, tradition, and intellectual seriousness, qualities that strongly influenced both his character and his approach to science. Max Carl Ernst Ludwig Planck was born in 1858 in the German city of Kiel into a respected academic family. Education was not merely encouraged in his household, it was a way of life. His father was a professor of law, and several relatives were theologians and scholars. From an early age, Planck was surrounded by discussions of ideas, ethics, and responsibility. This environment nurtured in him a deep respect for knowledge and a belief that intellectual work carried moral weight. As a child, Planck showed signs of exceptional intelligence, but he was not considered a prodigy in the dramatic sense. He was quiet, thoughtful, and methodical rather than flashy or rebellious. One of his earliest passions was music. He was an accomplished pianist and even considered a career in music at one point. This love for music played an important role in shaping his scientific mind. Music taught him harmony, structure, and balance qualities he later sought in the laws of nature. For Planck, the universe, much like music, followed deep and elegant patterns. During his school years in Munich, Planck encountered physics for the first time in a serious way. He was particularly drawn to mathematics and theoretical reasoning rather than experimentation. While many students found physics abstract and difficult, Planck found comfort in its logic and order. The idea that nature could be understood through precise mathematical relationships fascinated him deeply. When it came time to choose a university path, Planck decided to study physics, a choice that surprised some of his teachers. At the time, physics was considered a nearly complete field with little room for new discoveries. One of his professors even warned him that pursuing physics was unwise, as almost everything had already been discovered. Planck's response revealed much about his character. He replied that he did not wish to discover new things, but to understand what was already known. This statement perfectly captures his mindset. He was motivated by truth and understanding, not fame or revolution. Planck studied at the University of Munich and later at the University of Berlin, where he learned from some of the most respected physicists of the era. He absorbed classical physics deeply, especially thermodynamics, which would later become central to his work. Unlike some scientists who question authority early on, Planck trusted established theories. He believed that the laws of physics reflected an objective reality, and that these laws possessed an almost philosophical perfection. His early academic career was slow and challenging. After completing his doctorate, Planck struggled to find a permanent university position. For years, his work attracted little attention, and he lived modestly, dedicating himself quietly to teaching and research. This period tested his patience, but it also strengthened his discipline. He did not abandon physics, nor did he chase popularity. Instead, he focused on refining his understanding and contributing carefully, even when recognition was absent. What truly set Planck apart was his deep emotional connection to physics. To him, science was not just a profession, it was a moral pursuit. He believed that uncovering the laws of nature was a way of touching something universal and eternal. This belief gave him resilience during moments of doubt and frustration. Even when his work was ignored or misunderstood, he remained committed to the pursuit of truth. Planck's love for physics was also rooted in his belief in order. He lived in a time of rapid social and political change, yet he found stability in the idea that nature followed consistent laws. This belief later made his own discovery especially painful for him to accept, because quantum theory introduced uncertainty and discontinuity into a universe he believed to be orderly and predictable. Despite this inner conflict, his devotion to physics never weakened. He approached problems with patience, humility, and honesty. He did not force nature to fit his expectations. Instead, he allowed evidence and mathematics to guide him, even when they led to uncomfortable conclusions. This intellectual integrity was shaped during his early years, when he learned to value truth over personal comfort. Understanding Max Planck's early life helps us see why his contribution to science was so powerful. He was not driven by ego, rebellion, or ambition, but by a sincere love for understanding the universe. His disciplined upbringing, passion for music, respect for classical physics, and quiet perseverance all combined to shape a scientist capable of changing the foundations of human knowledge without ever intending to do so. In many ways, Max Planck's early life reminds us that revolutions are not always started by those who seek them. Sometimes they are born from patience, humility, and an unshakable love for truth. Centers on one of the most important scientific problems at the turn of the 20th century, blackbody radiation. Though the term may sound technical, this problem was at the heart of why classical physics began to fail, and why Max Planck's work became so revolutionary. Understanding this issue helps us see how a seemingly narrow question about heat and light led to a complete transformation of science. A blackbody is an idealized physical object that absorbs all radiation that falls on it and emits energy purely based on its temperature. When such an object is heated, it glows, first red, then yellow, and eventually white as the temperature increases. Scientists in the 19th century were eager to understand exactly how and why this emission of light occurred. The problem was not merely theoretical. It was grounded in real experiments involving furnaces, heated metals, and cavities that trapped radiation. Physicists attempted to describe blackbody radiation using classical laws of physics, especially thermodynamics and electromagnetism. These theories worked well at low frequencies, accurately predicting how much energy would be emitted as heat. However, as scientists extended their calculations to higher frequencies, particularly in the ultraviolet range, the equations produced alarming results. Classical theory predicted that a blackbody should emit an infinite amount of energy at high frequencies. This prediction was clearly absurd. In reality, objects do not release infinite energy, no matter how hot they become. Experiments consistently showed that energy emission increased with frequency up to a point, reached a peak, and then dropped sharply at higher frequencies. This stark mismatch between theory and observation became known as the ultraviolet catastrophe. It was not just a minor error, it was a complete breakdown of classical physics. The ultraviolet catastrophe deeply troubled physicists because it challenged the very foundations of their understanding. Classical physics assumed that energy could vary smoothly and continuously. According to this view, a system could release any amount of energy, no matter how small or large, without restriction. This assumption worked well for large-scale phenomena, but failed completely when applied to microscopic processes like radiation at atomic scales. Several scientists attempted to solve the problem by modifying existing equations or introducing clever mathematical tricks. Some partial solutions worked for specific frequency ranges but failed elsewhere. No single classical approach could explain the entire radiation curve observed in experiments. The problem refused to go away, growing more serious as experimental measurements became more precise. Max Planck approached this problem not as a rebel, but as a loyal defender of classical physics. He believed deeply in thermodynamics and was determined to preserve its validity. His initial goal was simply to derive an equation that fit the experimental data, not to change the fundamental nature of physics. In his search for a solution, Planck made a bold and unexpected assumption, one that even he found difficult to accept. Planck proposed that energy is not emitted continuously, but in discrete units. He suggested that oscillators within a heated object could only emit or absorb energy in fixed amounts proportional to their frequency. These tiny packets of energy later became known as quanta. This assumption allowed Planck to derive a formula that perfectly matched the experimental blackbody radiation curve across all frequencies. What made this idea so radical was that it directly contradicted classical beliefs. If energy could only exist in discrete amounts, then the smooth, continuous picture of nature was incomplete. Planck himself saw this as a mathematical compromise rather than physical reality. He believed that the quantization of energy was a temporary assumption that would eventually be explained by classical theory. Yet the success of Planck's formula could not be ignored. For the first time, physicists had a single equation that accurately described blackbody radiation. The ultraviolet catastrophe disappeared entirely under this new approach. What classical physics could not solve, a simple but revolutionary assumption had resolved. Over time, it became clear that Planck's solution was not just a convenient trick. It revealed a fundamental truth about nature. Energy at the atomic level behaves differently from energy at the human scale. The blackbody radiation problem had exposed the limits of classical physics and opened the door to a new way of thinking about reality. This problem also highlighted a crucial lesson in scientific progress. Sometimes, the most important discoveries arise not from grand questions, but from stubborn details that refuse to fit existing theories. Blackbody radiation was one such detail, quietly challenging the confidence of 19th century physics until someone had the courage to rethink its assumptions. The unsolved problem of blackbody radiation marked the exact point where classical physics began to break, and quantum theory was born. It showed that nature does not always behave in the smooth, predictable way humans expect. Instead, at its deepest level, the universe operates in precise, structured steps that Max Planck first uncovered while trying to solve a single, troubling equation. What began as a technical problem about heat and light became the spark that ignited the quantum revolution, forever changing how we understand the physical world. Focuses on the moment when Max Planck introduced one of the boldest ideas in the history of science, the concept that energy is quantized. This idea did not emerge from imagination or philosophical speculation, but from Planck's intense struggle to reconcile theory with experimental evidence. It represents the exact turning point where classical physics quietly gave way to an entirely new understanding of nature. For centuries, energy had been understood as something continuous. Whether it was heat flowing through an object, light spreading through space, or sound moving through air, energy was assumed to vary smoothly without interruption. This belief was deeply rooted in classical physics and had worked extremely well in explaining everyday phenomena. No one questioned it seriously until blackbody radiation forced scientists to confront its limitations. As Planck worked on the blackbody radiation problem, he realized that all classical approaches failed to produce accurate results across all frequencies. The experimental data was clear and reliable, yet the theories refused to cooperate. Faced with this dilemma, Planck made a decision that he later described as an act of desperation. He introduced an assumption that violated everything physics stood for at the time. Planck proposed that the tiny oscillators responsible for emitting radiation inside a heated object could not release energy in arbitrary amounts. Instead, they could only emit or absorb energy in fixed, discrete packets. The size of each packet was directly proportional to the frequency of the radiation. This relationship introduced a new fundamental constant of nature, now known as Planck's constant, which defined the smallest possible unit of action in the physical world. This idea of quantization was shocking because it implied that energy behaves more like money paid in coins than water flowing in a stream. Just as you cannot pay half a coin, an atom could not emit half a quantum of energy. Energy changes occurred in jumps, not smooth transitions. This was completely foreign to classical thinking. What makes this moment so extraordinary is that Planck himself did not believe in the physical reality of quantized energy. To him, it was merely a mathematical assumption that happened to work. His goal was not to change physics, but to make the equations fit the data. In his own words, he saw this step as a purely formal assumption. He believed that a deeper classical explanation would eventually be found. Despite his personal doubts, the success of the idea was undeniable. Planck's new formula perfectly matched experimental observations of blackbody radiation at all frequencies. The ultraviolet catastrophe vanished entirely. For the first time, theory and experiment were in complete harmony. What centuries of classical physics could not achieve, this single assumption had accomplished. However, the true significance of energy quantization did not become clear immediately. Many physicists initially viewed Planck's idea with skepticism or indifference. It seemed too strange, too artificial, and too disruptive to be taken seriously. Yet science has a way of revealing truth through persistence. Just a few years later, Albert Einstein took Planck's idea seriously and applied it to the photoelectric effect. Einstein proposed that light itself was made of quantized packets of energy, later called photons. This bold step confirmed that quantization was not limited to oscillators in matter, but was a fundamental property of light. Einstein's work provided strong experimental evidence that Planck's assumption reflected physical reality. From that point onward, the idea of quantized energy spread rapidly. It became the foundation for understanding atomic structure, electron behavior, and chemical reactions. The quantum concept explained why atoms are stable, why electrons occupy specific energy levels, and why matter emits and absorbs light in precise patterns. None of these phenomena could be explained without Planck's original idea. What makes the birth of energy quantization especially powerful is the mindset behind it. Planck did not seek to be revolutionary. He followed the evidence honestly, even when it led him away from his deepest beliefs. This intellectual integrity is one of the greatest lessons of his work. True scientific progress, as Planck demonstrated, requires the courage to accept results that challenge even our most trusted assumptions. The quantization of energy marked the beginning of a new era in physics. It shattered the illusion that nature is always smooth and continuous, and revealed a universe built on discrete steps and precise limits. Though Planck may not have fully embraced the implications of his discovery at the time, history would prove that his bold idea was the key that unlocked the quantum world. In introducing energy quantization, Max Planck did more than solve a technical problem. He changed the language of science itself, opening a doorway to a deeper and more mysterious understanding of reality. Marks the true birth of the quantum concept, the moment when Max Planck's mathematical solution evolved into a revolutionary idea that redefined how scientists understand the universe. Although Planck initially viewed his discovery as a technical fix, history would reveal that he had unknowingly opened the door to an entirely new framework of physics, one that challenged classical assumptions at their core. At the turn of the 20th century, physics stood at a crossroads. Classical theories had reached their limits, yet most scientists were reluctant to abandon them. When Planck introduced his radiation formula in 1900, many viewed it as an elegant equation rather than a radical statement about nature. The idea that energy came in discrete units seemed strange and unnecessary to most physicists, especially because Planck himself treated it cautiously. However, the very success of Planck's formula forced scientists to confront its deeper meaning. Unlike previous models, it worked universally. It did not require separate rules for low and high frequencies. One assumption, energy quantization, explained the entire blackbody radiation curve. This level of precision was impossible to ignore. Slowly, the scientific community began to realize that something fundamental had changed. The true shift occurred when the quantum idea moved beyond blackbody radiation and began explaining other phenomena. In 1905, Albert Einstein applied Planck's concept to light itself. He proposed that light was not just a wave, but also behaved as a stream of energy packets, later called photons. This explanation successfully accounted for the photoelectric effect, where light striking a metal surface ejects electrons only if the light has sufficient frequency, regardless of intensity. Classical physics could not explain this, but the quantum concept could. Einstein's work transformed Planck's cautious assumption into a bold physical reality. Energy quanta were no longer confined to oscillators in matter. They were a fundamental property of light. This marked the true birth of quantum theory as a new way of thinking, not just a mathematical trick. Nature, it seemed, was not continuous at its deepest level. As the quantum concept gained traction, it began reshaping the understanding of atoms. Niels Bohr built on Planck's idea to propose a model of the atom in which electrons occupy specific energy levels and can only jump between them by absorbing or emitting quanta of energy. This explained atomic spectra with remarkable accuracy. What once appeared as random lines of color now made sense through quantized transitions. This new framework introduced a profound shift in how scientists viewed reality. In classical physics, objects could exist in any state with any amount of energy. In quantum physics, only certain states were allowed. The universe operated more like a finely tuned system of rules than a smooth continuum. This idea was unsettling, even disturbing, to many physicists who had been trained to believe in continuity and determinism. Max Planck himself watched this transformation with mixed emotions. While he recognized the success of the quantum concept, he struggled to accept its philosophical implications. He famously remarked that a new scientific truth does not triumph by convincing its opponents, but because its opponents eventually die and a new generation grows up familiar with it. This observation reflected his own experience of watching classical physics gradually give way to quantum thinking. The birth of the quantum concept also changed the role of the observer in science. Measurements at the quantum level were no longer passive. The act of observation itself affected outcomes. This idea would later be developed by physicists like Heisenberg and Schrödinger, but its roots lay in Planck's original insight, that energy and matter behave differently at the smallest scales. What makes this moment in history so powerful is that it was driven by evidence, not ideology. The quantum concept emerged because nature demanded it. Experiments forced scientists to abandon comfortable assumptions and accept a stranger, more complex reality. Planck did not invent quantum theory to be revolutionary. He discovered it by refusing to ignore facts. The birth of the quantum concept marked a turning point not only in physics, but in human thought. It showed that reality is not always intuitive, that truth can exist beyond common sense, and that even the most successful theories are temporary. From this moment forward, science would never again assume that understanding the large automatically meant understanding the small. By introducing the quantum idea, Max Planck unknowingly reshaped the foundation of modern science. What began as a solution to a narrow problem became a new lens through which humanity views the universe, a lens that continues to reveal deeper mysteries and extraordinary possibilities. Focuses on the initial rejection and doubt that Max Planck's idea faced from the scientific community. Revolutionary ideas rarely receive immediate acceptance, and the birth of quantum theory was no exception. In fact, one of the most remarkable aspects of Planck's discovery is how slowly its significance was recognized, even by Planck himself. The resistance it encountered reveals how deeply rooted classical thinking was and how difficult it is for science to let go of familiar beliefs. At the beginning of the 20th century, classical physics was not just a set of theories. It was a world view. It had successfully explained motion, energy, electricity, and magnetism with extraordinary precision. Generations of scientists had built their careers on the assumption that nature was continuous, deterministic, and predictable. Against this backdrop, the idea that energy existed in discrete packets sounded unnatural and unnecessary. When Planck presented his radiation law in 1900, most physicists treated it as a clever mathematical solution rather than a statement about reality. Many believed that the quantization of energy was merely a formal trick, useful for calculations but not physically meaningful. This interpretation was reinforced by Planck's own cautious attitude. He did not aggressively promote the quantum idea as a new principle of nature, which made it easier for others to dismiss its deeper implications. Some scientists actively resisted the concept. The notion that energy could not be divided infinitely clashed with centuries of scientific intuition. Critics argued that quantization violated fundamental principles of mechanics and electromagnetism. Others felt uncomfortable with the loss of continuity, which had been a cornerstone of physical reasoning. For them, Planck's idea seemed like an admission of failure rather than progress. Another reason for skepticism was the lack of immediate experimental evidence outside blackbody radiation. While Planck's formula matched radiation data perfectly, it did not yet explain a wide range of phenomena. Without broader applications, many physicists saw no reason to abandon classical theories that had proven reliable in countless situations. Even Max Planck experienced deep internal conflict. He had devoted his life to classical physics and believed strongly in its principles. Accepting quantization meant admitting that the foundations of physics were incomplete. For years, he hoped that a classical explanation would eventually emerge to replace the quantum assumption. This hesitation highlights an important truth. Discovering something new does not always mean accepting it immediately. The turning point began slowly, not with Planck, but with others who were more willing to embrace radical conclusions. Albert Einstein was among the first to recognize the physical reality of quanta. His explanation of the photoelectric effect in 1905 provided strong evidence that light itself behaved in quantized units. This result could not be explained by classical wave theory and forced physicists to reconsider their assumptions. Despite Einstein's success, resistance remained strong. Many leading scientists, including some who later contributed to quantum theory, were initially skeptical. The idea that light could behave as both a wave and a particle seemed contradictory. Classical physics offered no framework for such duality, and the lack of intuitive understanding made acceptance even harder. As more experimental evidence accumulated, the doubts gradually weakened. Atomic spectra, specific heat measurements, and later electron behavior all pointed toward quantization. Each new result added pressure on the classical framework, making it increasingly difficult to ignore the quantum explanation. Planck's role during this period was unique. Rather than defending his idea aggressively, he remained measured and thoughtful. He supported experimental work and encouraged open discussion, but he did not force conclusions. This quiet persistence allowed the idea to mature naturally within the scientific community. The initial rejection of quantum theory illustrates a powerful lesson about scientific progress. Science is not driven solely by logic and data. It is also shaped by human habits, beliefs, and emotional attachments. Even the strongest evidence can be resisted when it threatens deeply held views. By the time quantum theory gained wider acceptance, the scientific landscape had changed dramatically. The doubts that once surrounded Planck's idea became stepping stones toward a richer understanding of nature. What was once dismissed as a mathematical curiosity became the foundation of modern physics. The skepticism faced by Planck's discovery reminds us that truth does not always arrive with applause. Sometimes it enters quietly, challenges everything, and waits patiently for the world to catch up. Explores how Max Planck's idea transformed modern physics and reshaped humanity's understanding of the universe. What began as a modest attempt to solve a technical problem soon became the foundation of an entirely new scientific era. The impact of Planck's work did not remain confined to one equation or one field. It spread across physics, chemistry, and technology, altering the course of science forever. Once the quantum concept gained acceptance, it became clear that classical physics described only part of reality. Classical laws worked well for large objects moving at ordinary speeds, but they failed at atomic and subatomic scales. Planck's discovery revealed that nature operates differently at these levels, following rules that are precise yet fundamentally different from classical expectations. One of the earliest transformations occurred in atomic physics. Before quantum theory, scientists had no reliable explanation for why atoms were stable or why they emitted light at specific wavelengths. Classical models predicted that electrons orbiting a nucleus should continuously lose energy and collapse inward, making atoms unstable. Quantum theory solved this problem by introducing quantized energy levels. Electrons could exist only in specific states and could change energy only by jumping between them. This insight explained atomic stability and spectral lines with remarkable accuracy. Quantum theory also transformed the understanding of light and matter. The classical debate over whether light was a wave or a particle had lasted for centuries. Quantum physics revealed that light exhibits both behaviors, depending on how it is observed. This wave-particle duality extended to matter itself, showing that electrons and other particles also behave like waves under certain conditions. This discovery blurred the boundary between particles and waves, challenging classical categories. Another major transformation was in the concept of determinism. Classical physics assumed that if the present state of a system was known precisely, its future could be predicted with certainty. Quantum theory replaced this certainty with probability. The outcomes of events at the quantum level could only be predicted statistically, not exactly. This shift was deeply unsettling, as it suggested that uncertainty was not a limitation of measurement, but a fundamental feature of nature. This new understanding led to the development of quantum mechanics, a complete mathematical framework created by scientists such as Heisenberg, Schrödinger, and Dirac. Their work formalized Planck's initial insight into a powerful theory capable of predicting experimental results with extraordinary precision. Despite its abstract nature, quantum mechanics became one of the most successful theories in the history of science. The influence of Planck's idea extended beyond physics into chemistry. Quantum theory explained how atoms bond to form molecules and why chemical reactions occur. It provided the foundation for understanding molecular structure, reaction rates, and material properties. Modern chemistry, materials science, and nanotechnology all depend on quantum principles. Perhaps the most visible impact of Planck's discovery lies in technology. Quantum theory made possible the invention of semiconductors, which form the basis of computers, smartphones, and digital communication. Lasers, used in medicine, industry, and telecommunications, rely on quantum energy transitions. Medical imaging techniques, such as MRI, are rooted in quantum behavior. Even the devices used to measure time with extreme precision, such as atomic clocks, are based on quantum principles. Beyond practical applications, quantum theory changed how humans think about reality itself. It challenged the idea that the universe is entirely objective and independent of observation. At the quantum level, measurement affects outcomes, raising deep philosophical questions about the role of the observer. These questions continue to inspire debate among scientists and philosophers alike. Max Planck did not live to see all the technological marvels that grew from his work, but he witnessed the transformation of physics during his lifetime. He saw his once controversial idea become central to science, yet he remained humble, emphasizing that scientific progress is a collective effort built over generations. The transformation of modern physics through Planck's idea shows how a single insight can ripple across centuries. It reveals that progress often begins with a small, precise question and leads to profound changes in understanding. Planck's work did not just add new knowledge, it redefined the rules by which knowledge is created. By changing how scientists understand energy, matter, and information, Max Planck reshaped modern physics and laid the groundwork for the technological world we live in today. His legacy is a reminder that the deepest revolutions often begin quietly, with one honest attempt to understand the truth, highlights Max Planck's profound influence on Albert Einstein and the generations of scientists who followed. While Planck himself was cautious and deeply rooted in classical traditions, his discovery became the spark that ignited the minds of younger thinkers who were willing to explore its radical implications. In many ways, Planck did not just introduce a new idea, he opened a door that others courageously walked through. Albert Einstein was among the first to recognize the true significance of Planck's quantum concept. In 1905, a year often called Einstein's miracle year, he published several groundbreaking papers, one of which directly built upon Planck's work. Einstein proposed that light itself is made of discrete packets of energy, later known as photons. This idea went far beyond Planck's original assumption, which had limited quantization to oscillators in matter. By applying quantization to light itself, Einstein transformed Planck's mathematical solution into a bold physical reality. Einstein's explanation of the photoelectric effect provided strong experimental confirmation of the quantum idea. When light shines on a metal surface, electrons are ejected only if the light has a minimum frequency, regardless of its intensity. Classical wave theory could not explain this behavior, but the photon concept did so perfectly. This work later earned Einstein the Nobel Prize, and it firmly established Planck's idea as a cornerstone of modern physics. Planck's influence did not end with Einstein. A new generation of physicists, including Niels Bohr, Werner Heisenberg, Erwin Schrödinger, and Paul Dirac, took the quantum concept and developed it into a complete theory. Bohr used quantization to explain atomic structure, showing that electrons occupy discrete energy levels. Heisenberg introduced matrix mechanics, emphasizing measurable quantities and uncertainty. Schrödinger developed wave mechanics, offering a different but mathematically equivalent description of quantum behavior. Dirac unified these ideas into a powerful theoretical framework. Each of these scientists built directly or indirectly on Planck's original insight. Without the idea that energy comes in discrete units, none of these developments would have been possible. Planck's constant appeared repeatedly in their equations, serving as a reminder of the small but crucial step that had started it all. What makes Planck's influence especially remarkable is the contrast between his personality and those he inspired. While Planck was conservative and hesitant to embrace the philosophical implications of quantum theory, many of his intellectual successors were bold and adventurous. They were willing to accept uncertainty, probability, and paradox as fundamental features of reality. Planck provided the foundation, and they built the structure. Planck also played an important role as a mentor and leader within the scientific community. As a respected professor, and later a leading figure in German science, he supported younger researchers and helped legitimize emerging ideas. His reputation lent credibility to quantum research during its early, controversial years. Even when he personally struggled with its implications, he defended the importance of open inquiry and rigorous experimentation. Beyond individual scientists, Planck's influence extended to the culture of science itself. Quantum theory encouraged collaboration across disciplines and national boundaries. It showed that progress often requires questioning deeply held assumptions and accepting counterintuitive results. This mindset became a defining feature of 20th century science. The legacy of Planck's influence is visible in every field touched by quantum theory. From particle physics to chemistry, from materials science to information technology, scientists continue to build upon principles that trace back to his work. Modern research into quantum computing quantum cryptography, and quantum communication still relies on Planck's constant and the idea of discrete energy states. Planck's influence also carries a moral dimension. He lived through periods of immense political and social upheaval, yet he remained committed to scientific integrity and intellectual honesty. His life demonstrated that science is not just about discovery, but about responsibility, perseverance, and respect for truth. The influence of Max Planck on Einstein and future scientists shows how one careful, honest idea can inspire generations. He did not dictate the direction of quantum theory, but he made it possible. His work reminds us that the greatest contributions to knowledge are often those that empower others to see further, think deeper, and challenge the boundaries of understanding. Through his influence, Max Planck became more than a discoverer. He became the quiet architect of modern science. Focuses on the personal humility of Max Planck, a quality that set him apart from many revolutionary figures in science. Despite igniting one of the greatest transformations in human understanding, Planck never saw himself as a conqueror of old ideas or a hero of modern physics. His humility shaped not only how he viewed his own work, but also how he interacted with others and endured immense personal hardship throughout his life. Max Planck approached science with a deep sense of responsibility rather than ambition. He believed that the laws of nature existed independently of human discovery, and that the role of a scientist was simply to uncover them honestly. This belief made him cautious about exaggerating his achievements. Even after quantum theory began reshaping physics, Planck continued to describe his discovery as a reluctant step rather than a triumphant breakthrough. Unlike many scientists who actively promote their ideas, Planck remained reserved. He did not claim ownership over quantum theory or insist that others accept his interpretation. Instead, he allowed the evidence to speak for itself. When younger scientists like Einstein expanded the quantum concept far beyond his original intentions, Planck did not resist or attempt to control the direction of the theory. He recognized that scientific truth evolves through collective effort, not individual dominance. Planck's humility was also evident in his attitude toward criticism. During the early years, when his ideas were met with skepticism or indifference, he did not respond with bitterness or defensiveness. He understood that resistance was a natural part of scientific progress. Rather than attacking his critics, he continued his work quietly, trusting that clarity would emerge over time. This humility extended beyond his professional life into his personal character. Planck lived simply and valued discipline, integrity, and moral responsibility. He believed that intellectual honesty was inseparable from ethical behavior. For him, science was not merely a career, but a calling that demanded patience and sincerity. Perhaps the most profound expression of Planck's humility can be seen in how he faced personal tragedy. His life was marked by extraordinary suffering. He lost his first wife at a young age, and later endured the deaths of all his children, including one son executed by the Nazi regime for his involvement in a plot against Adolf Hitler. Despite these devastating losses, Planck did not turn away from life or retreat into bitterness. Instead, he continued to serve science and society with quiet dignity. He believed that even in times of darkness, the pursuit of truth and reason remained meaningful. This belief reflected a humility that extended beyond ego. It was a recognition of human vulnerability and the limits of control over fate. Planck's response to the rise of Nazism further demonstrated his moral restraint. Although he did not openly rebel, he worked quietly to protect Jewish scientists and uphold academic integrity where possible. He understood the risks of confrontation, but chose to act within his limits. His actions were guided not by self-glorification, but by a sense of duty. Even after receiving the Nobel Prize and worldwide recognition, Planck remained modest. He often emphasized that his discoveries were the result of circumstances and collective knowledge rather than personal genius. He acknowledged the contributions of others freely and credited experimental evidence as the true guide of science. This humility also shaped Planck's philosophical outlook. He believed that science could reveal deep truths about nature, but he rejected the idea that humans could ever achieve complete understanding. To him, every discovery opened new questions. This perspective kept him grounded, even as quantum theory transformed physics in ways he had never imagined. Planck's personal humility offers a powerful lesson in an age often driven by recognition and competition. His life reminds us that greatness does not require loud claims or constant validation. True impact can emerge from quiet dedication, patience, and respect for truth. In the end, Max Planck's humility did not diminish his legacy. It strengthened it. By placing truth above ego and service above self, he embodied the highest ideals of science. His character stands as a reminder that the most profound revolutions are often led by those who never seek to be revolutionaries at all. Reflects on the lasting legacy of Max Planck, a legacy that extends far beyond his lifetime and continues to shape the modern world in profound ways. Although Planck lived in an era of chalkboards and early experiments, his ideas remain deeply embedded in the technologies, scientific thinking, and philosophical understanding of the 21st century. His contribution did not end with the birth of quantum theory. It became the foundation upon which much of modern civilization is built. At the core of Planck's legacy is the realization that nature operates according to limits. Planck's constant introduced a fundamental boundary to how small and how precise physical processes can be. This single concept reshaped science by revealing that energy, action, and information are not infinitely divisible. Today, this idea is central to every branch of modern physics, from particle physics to cosmology. Whenever scientists explore the smallest structures of matter or the earliest moments of the universe, they are guided by principles that trace back to Planck. One of the most visible aspects of Planck's legacy lies in technology. The digital world that defines modern life would not exist without quantum theory. Semiconductors, which power computers, smartphones, and the Internet, rely on quantum behavior of electrons in solids. Lasers, used in communication, medicine, manufacturing, and entertainment, operate through controlled quantum transitions. Even everyday tools like LED lights, GPS systems, and medical scanners are rooted in quantum principles, first unlocked by Planck's work. Beyond technology, Planck's influence transformed scientific thinking itself. Classical physics encouraged certainty and predictability, while quantum theory introduced probability and uncertainty as fundamental features of reality. This shift forced scientists to rethink what it means to know something. Measurement, observation, and limits became central concepts. Planck's legacy, therefore, is not only about equations, but about a new way of understanding knowledge and truth. Planck also left an institutional legacy. The Max Planck Society, named in his honor, is one of the world's leading research organizations. It supports groundbreaking research across physics, chemistry, biology, and the social sciences. This institution reflects Planck's belief in long-term curiosity-driven research free from immediate practical pressure. Through it, His commitment to knowledge continues to shape generations of scientists. Another lasting aspect of Planck's legacy is the example he set as a scientist and human being. He demonstrated that revolutionary ideas do not require revolutionary personalities. His patience, humility, and moral seriousness stand in contrast to the stereotype of the dramatic genius. Planck showed that careful reasoning, respect for evidence, and intellectual honesty can be just as powerful as bold speculation. Philosophically, Planck's work altered humanity's relationship with reality. Quantum theory challenged the idea that the universe is fully objective and independent of observation. It introduced questions about the role of the observer, the nature of causality, and the limits of certainty. These questions continue to influence philosophy, metaphysics, and even discussions about consciousness and information. Planck's legacy also serves as a reminder of how progress truly occurs. He did not intend to start a revolution. He simply refused to ignore a problem that classical physics could not solve. By choosing truth over comfort, he allowed science to move forward. This lesson remains relevant today, as scientists confront new mysteries that challenge current theories. Even in education, Planck's impact endures. Students across the world encounter Planck's constant early in their studies, often without realizing the depth of its significance. It represents the moment when humanity discovered that reality has a grain, a smallest step beyond which division is impossible. This idea continues to inspire awe and curiosity. Max Planck's lasting legacy is not confined to the past. It lives in every quantum experiment, every digital signal, and every attempt to understand the universe at its deepest level. His work reminds us that the universe is richer and more mysterious than intuition suggests, and that true understanding requires courage, patience, and humility. In the end, Max Planck's greatest legacy is this: he taught humanity that the deepest truths of nature are revealed not by certainty, but by the willingness to question even the most trusted beliefs. Through that lesson, his influence will endure for as long as humans seek to understand the universe.